Okay, let's keep going with this theme for a little while longer with the slideshow a little bit while longer. Okay, so when batteries are connected in series, which is, you know, I still haven't figured out yet if in your calculator, like if you have a TI-83 like mine or a TI-84, you know how you got to put them up, one right side up, one upside down, the right side. I don't know if that's in parallel or in series. Because it might only take that 1.5 volts to operate that calculator. I mean, it's working on very low voltage type circuitry. But anyway, but if you had five 1.5 volt batteries, then the total, if they're connected in series, you just add them up. V1 plus V2 plus V3 plus V4, and so you'd have a 6 volt, which makes sense to me. That'd be about 6 volts to operate the thing, and not 1.5 volts if you're hooked up in parallel. Now, batteries hooked up in parallel are connected in parallel. The total voltage does not change. Each battery supplies part of the total current. Okay, so the batteries don't change, but but what happens is you've got a lot more energy stored. Total voltage does not change. When batteries of equal are connected in parallel, their total voltage does not change. Each battery supplies part of the total current. Okay, so they apply part of the current that's needed to run that light bulb there. Okay, and we'll look at what current means too in this chapter, as a matter of fact. Okay, now here's some symbology that we say that you need to get to know. This stands for a battery. This is a resistor. This is a capacitor. You've already seen some of this. Two unconnected wires, or it can be this way. And these are two connected wires. You got them hooked like that. Open switch, closed switch, complete circuit here. All right. Now, current is the time rate of change, time rate of flow of charge. So the current I equals Q over T. Okay. So historically, the direction of the current has been taken from the positive to the negative. This is opposite the way the electrons flow. However, this seldom matters. Okay. So the actual electrons are flowing this way, and conventional current says it's going that way. All right. So we've got a few things to tie up here real quick. The EMF, we know the electromotive force. So these are September 7 notes, because today is September 6th, and you'll do this on September 7th. So V is the voltage, and in a battery we call it the EMF. The EMF, electromotive force. All right, and if a battery is hooked up in series, then the total voltage is equal to V1 plus V2 plus V3. All right. If it's in parallel, the total voltage is equal to V1 equals V2 equals V3. But what happens is the amount of charge stored in each, energy stored in each one of these batteries, it won't be depleted as fast. All right. And then the other equation that you learned real quick was this. You learned that the current, I, is equal to the amount of charge that flows through, like a resistor or something like that, divided by T. Okay? Q divided by T, which this is an amp, or amperes. It's measured in amperes. So I is equal to Q divided by T. All right, so let's take a quick look. Here's what I want to do. I wanted to take a quick look at what a battery actually looks like. So here we go. All right, I haven't turned this on yet. Notice we've got the voltage, the EMF right now is 0 inside this battery, and you're going to see the little battery fairies carrying the charge over to the negative, and then it's going to go through this resistor. Okay, it's going to go through this resistor. All right, so here we go. And the amps are cranking up. I've got 5 volts. Notice it's getting a little bit warmer. It's getting a little bit warmer. Here's our resistance. So here's flowing through here. This is supposed to be measuring how, if it's hot or cold. So here's our resistor, which you don't know anything about yet, but there's the resistance slowing it down. If our resistance goes really low, watch what happens. If our resistance goes really low, it starts to get really, really hot. Okay? And if we increase our voltage, it gets really, really hot and burns up so you need a resistor in there to keep it from burning up. And here's your little chemicals in here, the chemical, and it eventually runs out of energy. All right. So now we've reversed the voltage, so the charge is going the other way. Let's increase that. Now it's slowed way down. Slowing way down, it's cooled way off. Okay? This is your resistor, this is your battery, here's your charge flowing. Now this is showing you actually how the charge flows. When we do our calculations, we have the charge going this way. All right? Okay, so that's 2 equations we've learned so far. Well, we've learned about batteries in series, we've learned about batteries in parallel, and we've learned what amps are. Okay, so I is equal to Q over T. So an example would be, let's say a wire has 1.5 amps. Okay, how much charge flows in 15 seconds? Okay, well, 1.5 amps is equal to Q over 15 seconds. So you got 1.5 times 15, which would be 22.5 coulombs. Okay? So a lot of coulombs. So remember we talked about how a bolt of lightning is only like 20 coulombs, 15 to 20 coulombs? Yeah. So a lot of charge will flow through there. But the amperage is what will do you in. Now this is 1.5 amps. 0.5 amps will do you in. So that's pretty hot wire there. All right. Now let's talk about resistance.